Right. As you may remember, we are covering the discrete time version of the Fourier series, which is available to us as an analysis tool for discrete time periodic signals. So in this new representation of the discrete time case, we have an x of n, which is a periodic signal, and the period is capital N. And we say that it can be represented as a combination of n harmonics. So there are n distinct, capital N distinct harmonics with Fourier series coefficients, the corresponding Fourier series coefficients, capital N, right? With the Fourier series coefficients AK, sorry, where K is within a range of capital N. Those AKs can be expressed or can be achieved using the second formula that we see here in the second line, which is the mathematical tool that we may use. But of course we use it not for the sinusoids. For the sinusoids we have the famous Euler's expansion. Therefore their Fourier series expansion is obvious. Only for some unknown things we can use this formula to extract the Fourier series coefficient. So the first example that we have seen was a sinusoid where we didn't use that formula, because we know that a sine can be expressed as a combination of two complex exponentials, and once you have the complex exponentials, they correspond to the harmonics. You don't need anything else. That's the whole point, because we are trying to express, as you see, our signal as a linear combination of these complex exponentials with these coefficients. So those coefficients are here now. And these are complex exponentials. The complex exponentials indicate the frequency. The coefficients, AKs, indicate the scale of that corresponding harmonic at that particular frequency. Let's see another okay, we have seen two examples actually where we need to find or evaluate the fundamental period and the fundamental frequency. The fundamental period or frequency is a critical concept to determine the index of the Fourier series coefficient. And K, what is that K over there? For example, in this example we found it to be equal to K is equal to 6 and L is equal to 5. So we found 4 Fourier series coefficients. Now, I want to show you another related example, again as a linear combination of sines and cosines. X of n is equal to 1 plus sine 2 pi over capital N times n. This capital N is left to be parametric, so it can be any integer number, plus 3 cosine 2 pi over capital N, and plus another cosine term, this time 4 pi over capital N, and plus pi over 2. Okay. This plus pi over 2 is a phase, and as you may remember while I was solving the exam questions, I said that you could encounter such a question where some certain phase comes into the picture. If that thing comes into the picture, that will correspond to something, of course, but for this pi over 2, it's a very simple angle, and if you shift your cosine by an amount of pi over 2, as a matter of fact, what you get is nothing more than a sine. But let's forget about that. Let's consider it as an ordinary, random, or arbitrary phase, and how can we deal with such questions? I have to be honest about this question that it's not as difficult as it can be, because at least the periods are common here. So the common period is capital N, that's clearly. For the last thing, the period is n over 2, because 2 pi over n over 2 is what we have inside the last cosine term. So if one of the terms period is n over 2 and the others are n, then the period is automatically the least common multiple, which is n. If something is periodic with n over 2, it is also periodic with n. But if the periods of these three terms were different, like 5, 7, 6, things like that, you have to find the common, the least common multiple first to determine the indexes as well. That would be one further step for complication. It would be more complicated. So this is an example to indicate two important things that you have to consider. One of them is if the coefficient is not 1, then you have to be very careful about that. As you see in the second sinusoid, which is a cosine, you have 3 times cosine. You have to be careful about that. And then we have an angle term as well. So how are we going to handle those things? You have to just make an Euler expansion. I mean, that's the whole point. And then that Euler expansion automatically provides you the harmonics, and the coefficients of those harmonics will correspond to the Fourier series coefficients. Okay? So what are they? We have a 1 term. You may guess that it would correspond to A0, the DC term, and plus. Now let's think of this cosine, 3 times cosine 2 pi over capital N. That would make 3 over 2 times e to the j 2 pi over capital N plus 3 over 2 e to the minus j 2 pi over capital N. Okay? But now we have another. Now let's come back to this first sign. That sign is also having the same harmonics. The frequency of that sinusoid is the same. And what is that? Plus 1 over 2j e to the j 2 pi over n minus 1 over 2j e to the minus j 2 pi over capital N. So that corresponds to our sinusoid. And then we have the final thing, the third cosine. And then that third cosine is, how can we consider that? You have to consider the whole thing to be the angle, and cosine theta expansion in the Euler expansion case is known, and you have to use it. If you think of it as a theta, you will have something like this. You will have a plus 1 over 2. That 1 over 2 comes from the cosine. And then you will have something like this, e to the j 2 times 2 pi over n plus j pi over 2. So the whole thing that I write is in the exponent. Okay? And then you again write 1 over 2 e to the, again in a big parentheses, this time, okay, let's put the minus here, minus j 2 times 2 pi over n plus j pi over 2. Since I put the minus sign in the beginning of this parentheses, the minus reflects to all of these things. Now, all you have to do is you have to combine properly and extract the information which corresponds to the coefficient or the harmonic itself. When we combine, first of all, the two exponential terms in the first line here and the second line can be combined. It's the easiest to combine them first. So we have the whole thing to be equal to 1 plus. As you see, these two share a common exponent. So they correspond to the same harmonic. So we have to combine the corresponding coefficients, which is 3 over 2 plus 1 over 2j e to the j 2 pi over n. As you see, the Fourier series coefficient is a single term here, and that is 3 over 2 plus 1 over 2j. It's a complex number. That is the Fourier series coefficient. What k does it correspond to? We will look at that. And then we have plus another 3 over 2, this time minus 1 over 2j. As you see, I'm combining these harmonics, and the corresponding coefficients are 3 over 2 and minus 1 over 2j. And the harmonic is this, e to the minus j 2 pi over capital N n. Okay. How about the last line? How can I extract the information from there? Well, for that, you have to extract the constant angular phase term in the exponent together with this 1 over 2. I want you to take a look at this. It is 1 over 2 e to the j pi over 2. And that's it. Times e to the j 2 times 2 pi over n is one term, and plus another parenthesis, again 1 over 2, I'm writing this one now, and the angle is e to the minus j pi over 2. E to the j minus j 2 times 2 pi over capital N n. So this is my Fourier series representation that I have discovered using the Euler's expansion. And I just combined the appropriate terms as the Fourier series coefficients. Now I have to indicate which index it corresponds to. The fundamental frequency is 2 pi over capital N, because the fundamental period is capital N. So what is the index for the first one? It is 1 times omega 0, the fundamental period. Therefore, the corresponding Fourier series coefficient is the first Fourier series coefficient. It's A1. So let's now one by one write them. A1 is equal to 3 over 2 plus 1 over 2j. How about the second one at the top? That is when k is equal to minus 1, because it is e to the j 2 pi over n times k, and that k is minus 1 because it happened to be e to the minus j 2 pi over capital N. So now we can write a minus 1 to be equal to 3 over 2 minus 1 over 2j. Yep. No, the cosine is 1 over 2. It's a sine which makes 1 over 2j. Cosines are having real Fourier series coefficients, 1 over 2. Sine is an odd function, and they have purely imaginary 1 over 2j. And then, as you see in the third term, we have, by the way, let's not forget writing A0, that's equal to 1, the first 1 in the beginning, corresponds to the DC coefficient. Now the index that we have here is 2, because we have e to the j 4 pi over capital N, which makes 2 times 2 pi over capital N, and 2 pi over capital N is omega 0, therefore k is 2 here. So this whole expression is A2. And e to the j pi over 2 is j, by the way. So you can write it like j over 2. But if you're confused about that, just leave it to be e to the j pi over 2, if you wish. But it's j. What does that correspond to? Okay, let me finish this one, and then I will try to briefly explain how you can extract the information from a complex exponential form. The other one is with a minus 2 index, therefore we have a minus 2 to be equal to the negative of that in the exponent, and that would correspond to a minus j. So this is what you have. and we have 5 Fourier series coefficients. If you accurately describe all these coefficients, you can draw a box outside it and say that this is the answer. And with these answers, you will get full credit. Now, why is this j over 2, and how do we evaluate complex numbers? You must have seen complex numbers somewhere, but in case you don't remember, the situation is as follows. You draw a unit circle, okay, where this is 0 degrees, and then of course it must be in the form of radians, and then this is pi at the other side, and then at 2 pi you come back. So where is pi over 2? Pi over 2 is here, it's 90 degrees. So e to the j pi over 2 corresponds to this point. Okay, this is the point. And the real axis is the horizontal, the imaginary axis is the vertical. It's a unit circle, which means the radius is 1. So e to the j pi over 2 would correspond to this point, which is equal to 0. The real part of that coordinate is 0 plus j. The imaginary axis is the vertical axis. And what is e to the minus j pi over 2? That is a minus pi over 2 angle, which is traced in the reverse order, and that corresponds to this point. And the position of that on the vertical axis is minus 1, which makes a 0 minus j. Minus 1 times j. So can you guess, for example, what is e to the j pi over 4? Pi over 4 is just 45 degrees. It's this point. So you have to evaluate the real part and the imaginary part of these. And what are they? 1 over square root of 2 is here, and 1 over square root of 2j is here. Or j over square root of 2. If it is e to the 0, then it would be this point, and that would correspond to e to the 0 is 1. We all know it is 1 plus 0j, as you see. So you are just rotating on the unit circle to evaluate what the angle corresponds to. If you are having difficulty in these concepts, we will be using them all through the semester, so you may want to take a look at these things from math books if you wish, okay, in case you don't remember them. Although I said that the Fourier series coefficients are like this, you should always be aware that a k for this one is equal to a k plus some integer, let's say r times the period. We don't know the period n here, but if it is, for instance, 7, then a2 is equal to a9, and a minus 2 is equal to a5 as well. They are periodically repeating themselves. It's a very good idea to always put this expression afterwards as well. Okay, just use it to be complete. All right. Now let's open a new page, because we need to start with a new class of examples, and in this new class of examples we will need to use the formula for AK. And the example is as follows. It's like the first example that we have seen for the continuous time Fourier series, which requires calculation, and if you may remember, it was consisting of rectangular boxes periodically repeating themselves. So it's the same here. So we have a rectangular box here, like this. This is a box. The others are zeros. I'm only drawing the non-zero ones, and it starts from minus n1 up to n1. Notice that this n1 is not the period, it is just the width of the rectangular box, and then with a period it is repeating itself. For example, the same thing happens to be here as well, and this point is the period, that is the center of the box, and it is at capital N, it's not N1. So the period is equal to N, and the width of rectangle is equal to what? What is how wide is it? How many samples are there inside one rectangle? No, it's 2n1 plus 1, because there is one more in the center. So a rectangle is 2n plus 1 wide, and the period is capital N. Of course, I have drawn only 2 samples. They are repeating themselves. It's periodic. Like this. That's the. So what are the Fourier series coefficients is the question now we have to solve, and let's write the formula. The formula was 1 over n summation of n in a range of capital N, within a range of 1 period, x of n, this is the axis of n, let's not forget that, x of n e to the minus j k fundamental frequency, which is 2 pi over capital N times n. Okay, this was the formula. As you see in this formula, if you're using n as a running index, it will be in terms of k. It will not be in terms of n. Now, if you consider this signal, you will notice that, let me bring it down so that I can show you there. This sequence of length capital N can be best depicted from somewhere here, which is like minus n over 2 to n over 2, from here to here. It's a very bad idea if you try to evaluate the summation from 0 to n minus 1, capital N minus 1 up to here. Because then you will have 2 non-zero sequences at the left-hand side and at the right-hand side, which is difficult to express, to make it in a short, compact form. Instead, let's, as I said, take this summation and summation running index from minus n over 2 to n over 2 sort of thing. Let's take the period over there. And when we take it over there, the non-zeros will be only between minus n1 and plus n1, because the others in this summation will be zeros at the tails. The tails will be zeros in between. The compact rectangle starts at minus n1 and ends at plus n1. So we can write the summation like that. 1 over n, and from minus n1 up to n1. Only there x of n is non-zero. And as a matter of fact, there x of n is 1. So there is no need to even indicate that. And we can simply write the complex exponential, e to the minus jk 2 pi over capital N. So this summation is what we need to evaluate, and it looks not very easy. The power series or exponential summations are usually defined from 0 to somewhere as a summation. So it's a good idea to make a substitution like this. Let's say that m is equal to n plus n1. So let's not run n, but let's write the running index using m. Let's make a change of variables in the rule. So I'm substituting a new variable, which is m. And the summation will be 1 over capital N again, and the summation starts with m from 0 up to where? If I add n1 to the upper index of n1, it would make 2n1. So it's now from 0 to 2n1 with the new variable. But of course this n must be, n is equal to, as you see, m minus capital N1. So I have to replace wherever I see n by m. And that is e to the minus jk is the same. 2 pi over capital N is the same. It's the fundamental frequency. And instead of n, I have to write m minus n1. So this is my new running index. And that is 1 over n. M from 0 to 2n1. Okay. Now here we have two exponentials now. We have, the first one is e to the minus jk 2 pi over capital N m, and then I have e to the there is one minus from minus jk and one minus from minus n1. They cancel each other, so e to the jk 2 pi over capital N n1. Okay. Since it's a summation in the exponent, it's a multiplication of those two exponentials. Now the second exponential here is independent from m. Therefore it's a constant thing. If you know n, capital N or capital N1, and for a fixed value of k, it has nothing to do with m, so it can be taken out of the summation, which is containing m only. So it's out of the summation. 1 over n e to the jk 2 pi over capital N and 1. And then we have the summation m from 0 to 2n1 e to the minus jk 2 pi over capital N m. Now this summation is something that we are sort of familiar with. It's like e to the or any constant number, c to the minus m from 0 to some certain number. Do you remember that summation formula? It's a finite summation, it's not an infinite summation. And that finite summation, let me first write the coefficients or the scale. jk 2 pi over capital N and 1. Let me open a big parenthesis here, because the infinite summation works like this. In the numerator you have 1 minus the power series value reaching at the limit, the upper limit plus 1, divided by 1 minus the power. For example, if it is x to the n, the summation of x to the n is from 0 to m, let's say, is 1 minus x to the m plus 1 divided by 1 minus x. Do you remember that? If it is infinite series, it would be 1 over 1 minus x only. For that, you need to remember the series sums, which is, I believe, the second semester of calculus somewhere. Okay. This looks a little bit more complicated than that, but it corresponds to the same thing. 1 minus e to the minus jk 2 pi over capital N, and over here I have to say the upper limit is 2n1 plus 1. Okay? Divided by 1 minus e to the minus jk 2 pi over capital N. It's like 1 minus x to the n plus 1 divided by 1 minus x for the summation of x to the n from 0 to some limits. Okay. So this is the thing that we get. And for the curious, and in order to be precise, this garbage looking thing has a simplification. The simplification comes from the fact that we have the complex exponential positive and negative, and they balance each other with a minus sign in between. So e to the theta will come, and e to the minus theta will also come, and in between you have a minus sign. So e to the theta minus e to the minus theta. If there's a minus sign in between, that would correspond to a sign. If it's a plus in between two reciprocal or conjugate exponents, that would correspond to a cosine. So we expect to see sine here. And I'm skipping so many steps in between to finally give you the most compact form of this thing, not in the form of complex exponentials, but in terms of sines. And that is 1 over n sine 2 pi k over n times n1 plus 1 over 2 divided by sine pi k over n. Interesting. This is the result that we get after the simplifications of those messy looking complex exponentials. Now this thing is the most compact form, and you may realize that there's a problem about k is equal to 0 case. That is when the DC coefficient, because when k is equal to 0, sine pi k over n will be sine of 0, which is 0. But notice also that in the numerator it's the same 0 that we have. Because sine, the k is also in the sign, so it is sine 0 over sine 0 sort of thing, which is 0 over 0. That's an ambiguity. But by applying the Hospital's rule, you will not see that when you take the derivative of the signs, it's the same as looking at the insides only, and those k's will cancel. So just cancel the sign terms for k is equal to 0 case. And then k's will also cancel. The rest of the expression will correspond to k is equal to 0 case. And that is, by the way, we can write separately, to be equal to the average DC component. The average DC component evaluation by itself is quite simple. Look at the function. How many non-zero samples are there in a period? 2 and 1 plus 1 non-zeros. And what is the average then? You have to divide it by capital N. That would be the DC component. And if you just cancel out the k's, you will also see that it boils down to this. This is the simplest form of putting A0. So these are AK's, quite a complicated formula, and the others are A0s. The shape of this thing, do you remember the Fourier series coefficients envelope for the continuous case of rectangular boxes? A box here, and another box here, another box here. It was decaying with an oscillation. The decaying with an oscillation is this famous shape called sink shape. Okay, that's what we have said. Now this, believe it or not, is a similar shape. It is a sink shape. But it cannot be an accurate, a correct sink shape, because a sink shape starts from a peak and decays and oscillates and decays to infinity. However, we know that for discrete time periodic signals, AK is equal to AK plus N, or AK plus 2N, or in general AK plus R times N, right? So the Fourier series coefficients are periodic. So how can it be a sink and a periodic at the same time? It can't be. So it has to be a sink only in the central region, only within a period, sink-like shape, and then that sink-like shape is repeating itself. It is decaying and then increasing back to another sink, and then decaying, and then increasing back to another sink, and then decaying. That sort of a shape. Okay, so that is the shape, and I want you to be careful about or notice one very important thing. This is the first example that I have shown you that requires the evaluation of AK. Not from the Euler expression. The cosines and sines are simple. Without the cosines and sines, this is the first example that I have shown you. And look how complicated it is. Look at the top summation. It's pretty much complicated. And the simplification is still very complicated. The process is very difficult. So you should think of yourselves, by yourselves, like this. If this is the first example, then how will I ever be able to solve slightly more complicated question? It's difficult. This Fourier series thing is a messy process, and you have to use just you have to use not the this formula to evaluate AKs. When you try to literally write down the formula to evaluate AK, you fall into a trap. That's a very desperate situation. You can only, or you should only do it if you have nothing else to do. You have the formula, you have nothing else to do, put it inside the formula and try to simplify as much as you can. But that means you are desperate. Normally, you should consult to the properties that we have seen for continuous time case. Do you remember that? When you shift, that corresponds to a multiplication by an exponential. If you combine two signals, you have to combine their Fourier series representations. That's the linearity property. If you scale the signal, the Fourier series coefficients are also scaled. And things like that. There are many properties of Fourier series, and they are tabulated in the book as well. I didn't ask you any such property-related question in the first exam, and that's why I didn't give you I didn't let you to bring with you the tables from the book. But starting with the second examination and including the final, you will have to solve some more complicated problems. Therefore, you will need two things from each chapter. One of them is the list of properties table. What happens if I shift the signal? How will it behave? What happens if I accumulate or take the differential or the derivative? What would be the corresponding Fourier series coefficient? How do they change? That is one table that you will need from each chapter, and I am letting you to photocopy those pages from the book and then cut the table and bring it with you to the examination. Is that clear? That's a table that you will need, because you cannot remember all the properties. You have to remember all the properties that about their existence. You have to remember that such a property must be there and I need to use it, but you may not remember what it literally corresponds to. So you may forget that, and that's why you have to bring the table with you to solve questions. Otherwise, you cannot even solve the easiest question. Not this question, even this question, which is the first example. So that's one table that you can bring with you. The other table that you can bring with you is a list of common transformations. It is also listed in the book. Please look at your books for that. Common transforms. What are they? It's like this. If you have this rectangular thing, then its Fourier series coefficients are these. It's a common pair. There are a few more such cases which are quite difficult to extract by yourselves. And starting from them, you have to represent the question signal. I will draw you a question signal, and I will ask you to find the Fourier series coefficients. You have to just think that, okay, this signal that is asked in the question is a combination of two signals that I know, which are here. One of them is scaled by 2, the other one is shifted by 2, and then they are added to form this new signal. So how am I going to represent the Fourier series coefficients, AKs? You have to start from here, apply the properties of shifting and scaling, and then combining. And then you will say that, okay, sir, then this should be the Fourier series coefficient formula for the new question, for the signal in the question. That's how you have to attack. All right? Now, there is one last thing that I have to indicate regarding the discrete time Fourier series, and that is related with the LTI system response. To discrete time periodic signals. What I mean is this: the domain may look fantastic, but it's quite simple. We already know the system response to continuous time periodic signals, right? We evaluate the Fourier series coefficients, harmonics, and we draw them on the frequency axis. And I have to give you h omega, which is the filter. For example, in the example question, it was a cosine. It was cosine 3 omega, h of omega. So I need to give you h of omega, and then they are just scaled, multiplied by the corresponding frequency magnitudes of the filter. The outputs will have those multiplied or scaled Fourier series coefficients. And then you get those Fourier series coefficients, evaluate the corresponding harmonics, and then combine them. That would be your output. So the input-output evaluation of this thing is the same. You have to start with x of n, and then you evaluate ak and omega 0, and then you just pass it through a system which has frequency response to the system at some specific frequency. For example, if for low frequencies it's high or 1, and for high frequencies it is zeros, then that would correspond to a low pass filter. You remember that. Similar thing here. And the output will be bk is equal to ak times h of omega at omega is equal to k times the fundamental frequency. That is the frequency of the harmonic. That's how the bk's are scaled. Or you multiply ak with the corresponding h of omega at the corresponding frequency. And you have your new bk's. And from those new bk's, you reconstruct y of n is equal to bk e to the j k 2 pi over capital N n. You just combine them to reconstruct y of n. That's the way we have to work. But the difference, so there is not a fundamental difference between doing it in continuous time or doing it in discrete time. The difference is in the behavior of h of omega for the discrete time. Because notice that since the Fourier series coefficients AKs are repeating themselves, the situation is as follows. On the frequency axis, you have some AKs. Let's assume that they are like this, or let's put one more. So what is the period? Here, let's count. It's 8. The period is 8. And we have 8 distinct Fourier series coefficients. Let's draw them like this. Okay, just arbitrarily draw them. Then they must repeat themselves. And at the left hand side, let me draw it with a green. Etc. So it's going on like that. The red one at the right hand side, which is not very red looking, but it must be like this one, is a repetition of this black thing in the center, consisting of 8 coefficients, and the green ones at the left is also another repetition. So what I'm trying to say is that the Fourier series coefficients are repeating themselves. And I'm telling you that you have to multiply it with a discrete time system frequency response, h omega, you have to multiply. But the output must also be repeating itself. B case will also correspond to the similar frequency, or it's the same frequency oscillation with different harmonics. So what you have to deduce from here is that h of omega must also be periodic. So the low pass filter shouldn't be in the center only at 0. It must be repeating itself. If you have, let me draw it with the blue. If you have a low pass filter, for example, like this, to depict only the central low frequency harmonics and make the others 0, we know that the others here are also corresponding to the same coefficients. They are just repeated versions of that, which means that our filter shape shouldn't be a single blue like that, but it must be like this as well, or like this as well. So the h of omega must also be periodic. The question is, what should be the period? Can you guess what the period is? What this frequency corresponds to? Because here it is 0, and then it must repeat itself right there, right at that point. This is the 0 frequency. What is that frequency of the first red indicator? 8. Omega I'm talking about. I'm not talking about the indexes. K is equal to 8 is the answer here. K is equal to 8 means omega is equal to what? What is omega? Omega is equal to K times 2 pi over capital N. What is capital N? 8. So K is 8. 8 times 2 pi over 8. It is 2 pi. This point is 2 pi. It's like rotating unit circle. Alright? The filter has a frequency response which is 2 pi periodic. At every 2 pi it comes back to the same point. So this is a low pass filter, the dashed blue one is a low pass filter, and it is not like the low pass filters in continuous time. In the continuous time the low pass filter is this and all the others are 0. Because we have infinite frequencies. But in discrete time we don't have infinite frequencies. There is a maximum frequency available to us, and that maximum frequency is, it just happens to be here. That is the max frequency. And what is that equal to? It's the halfway between 0 and 2 pi. That is pi. Pi is the maximum frequency in discrete time. And we have to multiply respectively. The formulation for this dashed filter with respect to the impulse response in discrete time, we know that in discrete time the impulse response is h of n. With respect to h of n, what is this new h of omega? What's the formula for that? We will see, let's say after the break. Let's give a 15 minutes break right now. We will continue later.